burning oil well here, and this is an actual real problem, so I like these. And as I said, if there's wind, they can still use the calculus to model it, but it becomes a lot more parameters involved. So we're going to say no wind. Burning oil well. Burning oil well, or anything really. No wind. And if there's no wind, then the particulate matter will be distributed how? Evenly, and also more than just evenly. Yes, gets less dense. It's more dense near the well and gets less dense and less dense evenly at some rate, and it diminishes the further you get away. And further, it's in a circular pattern because there's no wind. Okay? So this is a nice problem to use calculus with because it's a rate of change as we go a distance r from our oil well. Okay, and then they'll always give you some kind of density model. They'll say the density with respect to distance r equals, in this example, it was 7 over 1 plus r squared. And we just say that this models density of particulate matter at any distance r. R from the fire. Okay. All right. So that's the setup. And this is the kind of problem that you cannot do without the calculus. I mean, it just won't happen. And that's why Newton really needed these types of problems. And Leibniz just did them for fun because he loved math. So anyway, so let's think about another ring here. Anywhere in here. Let me do another one. It's fine. So take some little ring here. Think about this ring. And if you make it really thin, the density is constant within it. Would you agree? Because it virtually has no distance. So within that tiny little ring, the density is going to be constant. If you make it really thin, which we do here. Okay? So then, let's write an expression for the area of that ring. Area, I don't know. I need a fiery color. Right. How hot it is, close to the fire, I don't know. Violets. Okay. Area of, depending on the chemicals, right, Jeremy? The area of the red ring or washer. Okay, what would that area be? Let's express that some way. Okay, we can say the thickness of the ring is delta R. We can definitely say that. What about the area of that ring? Riddle me this, Batman. What if we took that ring and made it like a licorice rope? A red licorice rope. Johnny, speak madness, Johnny. L equals 2 pi r, because we want to do it in terms of r, but you're right, it's diameter, And then what's the thickness of it? Delta R. Nice, guys. Everything is in terms of R. Beautiful. Beautiful, beautiful. And notice our density model is in terms of R. So this one is going to be sweet. Okay? So now, it would come out the same way. But, I want to expose you all to lots of different ones. We did a subtraction one the other day. I want you to think of this. You don't always have to do it the same way. You just have to think of a way to model area and then integrate to get totals or volume. Okay? No, it is cool. It is cool. It's neat. But Derek's right. You could have done one big circle minus one little circle, and it totally would have worked. Oh, do they? Okay. Okay. No, it's cool. And again, as I've always said, there's more than one way to get the right answer. Do it the way that you see best. But I want to expose you to as many as possible. So that's why I chose this. I thought it was kind of neat. Okay, so now, if we were trying to do the totals out here, anywhere, okay, in other words, stack up all those rings to get the total, what would we do? How about we write an integral, okay? Would be from what to what, Johnny? Stack them up. Integral sign means the sum of all those rings. Zero to, did I have a distance on this one? Oh, I just said R. Okay, so let's say out here, max R is 100, okay? Kilometers. Well, it's a fire. There's smoke. It's a big fire. 100 kilometers. It's out in the ocean. Yeah, it's one of those offshore deals. They're big. You've seen them. Okay. No, but this is smoke. Hey, there is one like that where it's an oil spill on the water. This is a fire, so it's airborne. Okay? No current, no wind. Yeah. So 0 to 100 kilometers, and then we would go, what? 2 pi r. This is what's really neat. dr, which we're going to need anyway. Then, what about our density? What did we have? 7 over 1 plus r squared. Okay, let's clean this up a little bit. Well, we can do it. Let's write it longhand first, and then we'll pull some stuff out. Okay, so we could go, this is then 14 pi r over 1 plus r squared dr. Yeah? Now let's make our lives easier. Pardon me? You can't. Alex, what can we do to make our lives easier before we integrate? We can more. No, that's a variable. We can't do that. Good try. We can take the pi out. No, 14. Jeremy, speak truth. We can take 14 pi out because those are constants. Times from 0 to 100 times r over 1 plus r squared dr. Okay, a couple different ways you could do that one. You could go r times the quantity 1 plus r squared to the 1/2, or no, to the negative 1. Ew, don't like that. Not when you've got a plus down here, and you can't divide any r's out also because it's plus. I think in a deal like this you better do a substitution. How about if we let u equal 1 plus r squared? Okay? Then we've got the derivative of u with respect to r equals what? 2r. Then we've got du equals 2r dr. This we can do. Okay, so now we've got 14 pi, and for now I'm going to go from a to b because I have a suspicion we're going to want to change the limits of integration to make this easier. Okay, of what? No, no more r's.
We have to, unless if we want to be able to put stuff in du, we need to make sure it's 7 pi. Because it's 2r.
Oh, yeah, because we've got a 2. Okay, he's right. Let's go. He's right. Let's go 7 pi out here and 2. No, just write another line. You don't have to erase it. Just write another line. Better. He's right. Let's go 7 pi. Is that the same thing? 7 times 2? 7 pi times 2? 14 pi. We're cool. We're cool. And now let's go u. What do you got? 1 over u, isn't it? 1 over u times, and then it says we be 2r dr. That's right. So what can I write here? Du, which is what we want. 1 over u du. Now, notice I can change my limits of integration to make my life easier. I don't have to, but, and again, you don't have to, but if you don't, then you've got to substitute back in after you're done. If you do, then you won't. So that's nice. Change limits of integration. Okay, we've said that f of original function was 1 plus r squared. So f of 0 equals 1 plus 0 squared equals what? 1. And f of 100. And again, I'm just taking this new function. I'm plugging in my limits, my old limits. F of 100 equals what? 1 plus 100 squared, which is, well, 100 squared is 10,000, so 10,001, right on. So those are my new limits. So now I've got 7 pi from, and I know that seems weird, but I think it'll make our lives easier in the end. But Johnny, you're right. You don't have to. From 1 to 10,001 of 1 over u du. And again, we did all that work ahead of time before we took the integral, and it'll make our lives easier. So what do we got? Good catch. I was going to smack you upside the head, Johnny. Natural log of u evaluated from 1 to 10,001. And again, you guys were laughing at me, but look how nice that is. Equals 7 pi. Now here, because we changed our limits of integration, we don't have to substitute back in. Because we changed our limits of integration, we do not sub back in for u. And that's important. It does. And you don't have to do that. But I think in this problem, it makes it a lot easier because we can just say the natural log, 7 pi times the natural log of 10,001. Somebody get that for me. Minus, no, I'm going to go like this. Minus 7 pi times the natural log of 1, which we all know that, equals, and then give me a number and we're done. times 7 pi. Well, since you've got a decimal already, times 3.1, well, you know, give me a straight decimal. 5.5, that's fine, whatever, 5.5. And those are in tons of particulate matter. And this is an actual kind of problem that people would do in the event of a disaster. You know, senators are going to say, how bad is this? And they're going to need to know how many troops to call out and start, you know, trying to help this and give health warnings to asthmatic people and stuff like that. So that's all we have. Questions? Oh, that would have been given in the beginning, and I probably didn't even say that. They'll give you a model, and they'll say the amount of particulate matter at any distance r between 0 and 100 kilometers is this, measured in tons of particulate matter. Johnny? Right. Well, the new ones don't represent a distance of kilometers, but they represent the equivalent of that given our new equation. That's all. They still represent a distance from the center, but it's just voiced in terms of our new equation. Instead of 1 plus r squared, it's 1 over u. Yes. Sometimes it's easier to sub back in, and sometimes it's not. And you just got to work enough of them to where you get convenient and comfortable with that. Okay, based on that, I think I should quit for today. I'm going to post